In this video, we will be going over the basics of trigonometry and the basic trigonometric functions sine, cosine, and tangent. The standard definition of sine, cosine, and tangent are in terms of side lengths in a right-angled triangle, but before I introduce them, I will present the definition in terms of the unit circle. The unit circle is a fundamental concept of trigonometry, and it's a circle with radius 1 centered around the origin. So that's the point 0, 0 on the Cartesian plane. So what's the definition of sine and cosine in terms of the unit circle? If we were to inscribe a right-angled triangle inside the unit circle and the x-axis as shown in the diagram with some angle theta between the longest side length, the one with the side length of 1, and the positive part of the x-axis in the counterclockwise direction, then sine of theta is the height of the triangle, or the side length shown in red. On the other hand, cosine of theta is the horizontal length of the triangle, or the side length shown in blue. Theta is a Greek letter which is used to denote angles, and it's this symbol here shown in the triangle angle. So the abbreviation of sine is sin, shown in one of the labels, and cosine is shortened as cos. So in simplest terms, you can think of sine and cosine as functions that take an angle as the input, and the output is a real number between -1 and 1 inclusive. The angle is denoted in degrees for the purposes of this video, but there's also another unit of measure for angles called radians, which allows us to drop the degree sign, but we won't cover that in this video. By the way, for the abbreviated versions of the sine and cosine functions, we sometimes just call it sin of theta and cos of theta. So let's go over a few simple examples. Let's say we want to find the values for sine of 50 degrees and cosine of 50 degrees. What we need to do is draw a right-angled triangle between the unit circle and the x-axis, where the angle between the positive part of the x-axis and the longest side length, called the hypotenuse, drawn in black, is 50 degrees. This inscribed triangle is shown in the diagram on the left-hand side. Once we have this triangle, we can determine that sine of 50 degrees is the height of the triangle, shown in red, and cosine of 50 degrees is the horizontal length of the triangle, shown in blue. So what are these values exactly? It's actually very hard to compute the values of trigonometric functions directly without a calculator, except for a few special cases, but you can see that it's definitely somewhere between 0 and 1, since they both have positive values, and the unit circle has a radius of 1. And in the first quadrant, both x and y coordinates have positive values. You can think of the x coordinate as the value of cosine theta, and the y-coordinate as the value of sine of theta. So let's do another example. Suppose we want to find the values of sine of 110 degrees and cosine of 110 degrees. The first thing to do is to draw a right-angled triangle between the unit circle and the x-axis, where the hypotenuse and the x-axis in the positive direction makes an angle of 110 degrees in the counterclockwise direction. So this is shown in the diagram on the right-hand side. So then the value of sine of 110 degrees is just the height of this triangle, which is the side length shown in red, and cosine of 110 degrees is just the horizontal length of this triangle, which is the side length shown in blue. Well, actually, cosine of 110 degrees has a negative value since the horizontal side length of the triangle lies in the negative part of the x-axis. So it's more accurate to say that the value is the side length shown in blue times a factor of -1. So cosine of theta is just the x-coordinate of the point in the unit circle. Now that I have introduced the idea of the unit circle and the triangle inside the circle, I will show another cleaner approach to defining the sine and cosine functions, which uses a similar concept. So here's another definition of the sine and cosine functions. If we want to find sine of 50 degrees and cosine of 50 degrees, we just need to draw a straight line from the origin to the circle, such that the angle between the line and the positive part of the x-axis is 50 degrees in the counterclockwise direction. Now we have to look at the point where the line intersects with the unit circle. The x-coordinate of the point is cosine of 50 degrees, and the y-coordinate of the point is sine of 50 degrees. In this case, both values are positive because the point lies in the first quadrant where the x and y coordinates both have positive values. If we want to find sine of 110 degrees and cosine of 110 degrees, we need to draw a straight line from the origin to the unit circle, such that the angle between the line and the positive part of the x-axis is 110 degrees in the counterclockwise direction, and that's the diagram on the right-hand side. The x-coordinate of the point where the line intersects the circle is cosine of 110 degrees, and the y-coordinate of the same point is sine of 110 degrees. So you can see that cosine of 110 degrees has a negative value while sine of 110 degrees has a positive value, since this point lies in the second quadrant where the x-coordinate has a negative value and the y-coordinate has a positive value. So out of interest, the point cosine of 50 degrees, sine of 50 degrees, is approximately the point 0.643, 0.766. And the point cosine of 110 degrees, sine of 110 degrees is approximately the point negative 0.342, 0.940. Like I said before, these values are hard to calculate by hand, and we usually need a computer or a calculator to help do these calculations for us. So this is essentially the same concept as the definition with the triangles, but we remove the triangle and the idea of side lengths to make it easier to explain the concept of negative values. In either case, it's clear that trigonometric functions like sine and cosine are geometrically defined in terms of the unit circle instead of algebraically, which is why they are sometimes called circular functions. Now let's cover the tangent function. The tangent function is usually abbreviated as tan, and it describes the slope of the line that goes from the origin to the unit circle. So tan of theta describes the slope of the line with an angle of theta between it and the positive x-axis in the counterclockwise direction. So in the diagram, it would be the slope of the hypotenuse, the longest side opposite to the right angle. So in the diagram, it would be this side over here with the length of 1. To get a visualization for what the value of tan of theta is, we can draw a tangent line to the circle at the point where the line meets the unit circle, so it's this point right over here, with the other endpoint being where it meets the x-axis. A tangent line is a line that just touches the circle or any curve at a single point without crossing over it. So what we do is we take this point over here, this is where the line intersects with the circle, and then we continue down here with our tangent line until it intersects with the x-axis here, and then that's where we stop. The length of the green line is the value of tan of theta when we're dealing with the first quadrant. So that's when theta is between 0 and 90 degrees. If we were dealing with other quadrants, we might have to multiply this by a factor of -1, but we won't worry about that now. So the reason this function is called the tangent function is likely because the definition of the function uses the concept of tangent lines. So don't confuse the two names. A tangent line is a line that touches a curve at one point without crossing over it. The tangent in the context of trigonometry is a function with a geometric definition, so that's the function we're introducing right now. These are two related but different concepts. So we can also define the tangent function in terms of sine and cosine. Tan of theta is equal to sine of theta divided by cosine of theta. This is because the tangent function describes the slope of the line, and slope is rise over run, or the change in y divided by the change in x. Since the length in the y direction is described by sine of theta, and the length in the x direction is described by cosine of theta, the slope is just sine of theta divided by cosine of theta. So tan of theta is just equal to sine of theta divided by cosine of theta. Alright, so we've covered a lot of theory, so now let's do an example. Suppose we're given the values. Sine of 50 degrees is approximately equal to 0.766, and cosine of 50 degrees is approximately equal to 0.643. And these are the values from the example that we did earlier. With these given values, we want to find the value of tangent of 50 degrees. So as we know, tan of theta is equal to sine of theta divided by cos of theta. So tan of 50 degrees is just equal to sine of 50 degrees divided by cos of 50 degrees. So if we plug in the values for sine of 50 degrees and cos of 50 degrees, we get 0.766 for the sine value and 0.643 for the cos value. So this is just 0.766 divided by 0.643. And if we plug this into a calculator, we end up with an answer that's approximate to 1.191. So if we are provided the approximate values of sine of 50 degrees and cosine of 50 degrees, we can use that to work out the approximate value of tan of 50 degrees. By the way, these values are very hard to work out by hand, so if we didn't have a calculator, or if we didn't have the sine and cosine values provided as part of the question, it would be exceedingly difficult to work out something like tan of 50 degrees. We've covered a lot of theory on what trigonometric functions are, so I will now introduce the definitions of sine, cosine, and tangent in terms of side lengths of a right-angled triangle. This is the definition you usually see when introduced to the topic. Suppose we have some angle theta in a right-angled triangle that's not the right angle itself. If we set a specific angle as theta, which is the angle we are working with, then we have three names for each side of the right-angled triangle. We have the hypotenuse, which is the longest side length, so that's the one opposite to the right angle, the opposite side, which is the one directly opposite to theta, and then there's the adjacent side, which is the one directly next to theta, but also not the hypotenuse. So you can think of the adjacent side as the one that is not the hypotenuse and also not the opposite side. So with these given names for each side in a right-angled triangle, we can define sine of theta to be opposite over hypotenuse, cosine of theta to be adjacent over hypotenuse, and tan of theta to be opposite over adjacent. So this means the value of each function is defined as the ratio of the specified lengths in a right-angled triangle. You may notice that these definitions match up with the unit circle definitions of trigonometric functions we covered earlier, since we defined sine of theta as the height of the right-angled triangle. Well, it turns out that was just the special case of sine of theta equals opposite over hypotenuse, since in the unit circle, the hypotenuse always has a side length of 1, so sine of theta just turns out to be the opposite side divided by 1, which is just the opposite side length, or the height of the triangle. The same thing applies for cosine of theta. The triangle inside the unit circle just has a cosine theta value of the adjacent side, or the horizontal length of the triangle, since the hypotenuse is 1, and division by 1 just results in the same number as the numerator, which is the adjacent side length. The tangent function is just the ratio between sine and cosine, so in the unit circle that would just be the value of the opposite side length divided by the adjacent side length, which are the values of sine and cosine respectively in the unit circle. You can use this acronym, SOHCAHTOA, to help you remember the definitions of trigonometric functions. So in each acronym, the first letter is the first letter of the trigonometric function. So S is the first letter of sine, C is the first letter of cosine, and T is the first letter of tangent. And then the O stands for opposite, H stands for hypotenuse, and A stands for adjacent. So for example, SOH stands for sine, opposite, and hypotenuse. So that means sine is defined by opposite over hypotenuse, and so on. So just remember this acronym, SOHCAHTOA. It really helps you remember the definitions of these trigonometric functions. Alright, so let's do an example. Suppose we're given this triangle. It's a right-angled triangle with side lengths 3, 4, and 5, and we want to find the values of sine of theta, cosine of theta, and tangent of theta, where the theta angle is this angle right over here. So this is actually a real triangle, because whenever we have a right-angled triangle and two of the side lengths are 3 and 4, then the hypotenuse, the longest side that's opposite to the right angle, is going to equal 5. And this is actually a well-known triangle, and we can use the Pythagorean theorem to figure out the side lengths. Well, anyways, what we want to do is look at theta, and then if we want to find sine of theta, we should work out what opposite over hypotenuse is equal to. So if we look at this theta value, well, the opposite side length is 4, and the hypotenuse is 5, because that's the longest side length. So using the definition, we can work out that sine of theta is equal to 4 over 5. So 4 is the opposite, and 5 is the hypotenuse. Now if we want to work out cosine of theta, we need to do adjacent over hypotenuse. So adjacent is the side length that's not opposite to theta, and it's also not the hypotenuse. So the side length with 4, that's the opposite, and then 5 is the hypotenuse. So the adjacent is 3. So cosine of theta is equal to 3 divided by the hypotenuse, and we know that the hypotenuse is equal to 5. And then now we just need to work out tangent of theta. Well, tangent of theta is equal to opposite over adjacent. So the opposite side length, as we've noted before, is equal to 4, and adjacent was the 3 right over here, so it's 3. So it's 4 over 3. So these are the values of sine of theta, cosine of theta, and tangent of theta with respect to this specific triangle. And another thing that you can notice is that tangent of theta is definitely equal to sine of theta divided by cosine of theta. Because if we take 4 over 5 and then we divide that by 3 over 5, well, the 5s will cancel out, and that's just 4 over 3. So it's 4 over 3 right here. So that's the same one. So we've covered a lot of theory, as well as an example with a triangle. The unit circle is what allows us to determine the actual values of the trigonometric functions sine, cosine, and tangent. But the key problem covered is how to find the values of sine of theta, cosine of theta, and tangent of theta when given a specific right-angled triangle and a specific angle set as the theta. It's also helpful to use the acronym SOHCAHTOA to remember the definitions of sine, cosine, and tangent.